Welcome to Basic Mathematical Analysis class. Last class we had discussed some of the theorems on limit of sequences. This is the continuation of your last class. That is, today also we are going to discuss some theorems on limit of sequences. Last class we have seen the limit of some of the sequences, that is namely when you're having two sequences x and y, we have found out what's the limit of x plus y and x dot y, x minus y, and if z is a non-zero sequence of real numbers and that z is converging to some z that is not equal to 0, then the sequence x by z that also converges to x by z, right? That is, the sequence xn converges to x and sequence yn converges to y. Oh, we have used the other way of notation, right? So notation is, so sequence xn converges to x and sequence yn converges to y. Then we have seen that the sequence xn plus yn, which will converges to x plus y, and sequence xn minus yn, which is convergence to x minus y. Next was xn yn. This converges to xy, xy, and the sequence for some c belongs to R means c into xn will converges to cx. Now if z equal to zn such that zn not equal to 0 for every n, then if your sequence zn converges to z with z not equal to 0, then your sequence xn by zn that will converges to x by z. So these and all the facts we have seen in the last class, right? These all we have seen in the last class. Today we will discuss, right? In this case we have taken only two sequences. Suppose there are many sequences and we are finding the sum of that all sequences. Will it be converges to the sum of the limits? Answer is yes. Okay, so we can prove that using mathematical induction method. So just we will write it as a remark here. Remark. Remark. Now by using induction, we get if A equal to an, B equal to bn, etc., some z equal to zn are convergent sequences of real numbers then their sum we are writing it as a plus b plus c plus extra plus z, and this equal to, when you're writing as a sequence, it should be an plus bn plus extra plus zn, right? is a convergent sequence, is a convergent sequence and and we are finding limit of the sequence an plus bn plus extra plus zn. This value should be equal to limit of the sequence an plus limit of the sequence bn plus etc plus limit of the sequence zn. Also we can have this result for the differences of sequences and for the product of the sequences too. So also limit of product, I'm writing an bn cn extra zn. So this is the product of the sequence, that is again is equal to limit of an into limit of bn into extra into limit of zn. Now suppose this all are going to be the same sequence, all are an. So also a an an extra some an. I'm taking this as k times k times. So what it should be? This should be equal to limit of an into limit of an extra limit of again an, right? Now this is equal to limit of an, how many times will come? And k times, so I'll raise to k, right? So what does this means? This we are getting uh, limit of this, right? So I should write limit. So limit of the sequence is nothing but an raised to k. An raised to k is equal to limit of an raised to k. So limit of an raised to k is equal to limit of an all raised to k. I should write like this. Limit of an all thing raised to k. So this is the one thing we want to note it here. Next is theorem 3.2.4 theorem. 3.2.4 theorem. If x equal to xn is equal to xn is a convergent sequence, is a convergent sequence of real numbers and if xn is greater than or equal to 0 for all n belongs to n, for all n belongs to n, then x equal to limit of xn, and this value is also greater than or equal to 0. That means when you're having a sequence in which every term is greater than or equal to 0, then the limit of that sequence is also greater than or equal to 0. So how to prove it? So we should assume a sequence. So suppose x equal to xn is a convergent sequence, with xn converges to x, and suppose that xn is greater than or equal to 0, right? Now if this limit, if x is less than 0, we want to prove that x is greater than or equal to 0, so we're taking the quadratic part, right? Or the we want to get a contradiction. Now if this x is less than 0, then minus x is positive, right? Minus x is positive. So let your epsilon is equal to minus x. I'm putting my epsilon is equal to minus x. Now since our sequence xn converges to x, there exists a k belongs to the set of natural numbers such that modulus of xn minus x is less than epsilon. Modulus of xn minus x is less than epsilon. Or that is, you can have this as minus epsilon less than uh, sorry less than xn minus x less than epsilon, or that is, you get x plus epsilon less than xn less than x minus epsilon, this one, right? X minus epsilon less than xn less than x plus epsilon, right? For all n greater than or equal to k. So we are having for all n greater than or equal to k, n minus epsilon less than xn less than x plus epsilon. So in particular, for n equal to k also this should be true. We have xk is less than x plus epsilon, right? We are having this part, xn is less than x plus epsilon. Xn is less than x plus epsilon. Now taking this part, for n equal to k means xk is less than x plus epsilon we will get, right? Now what is epsilon? Epsilon is equal to minus x. So when you are adding this, so this is equal to x plus minus x, that's equal to 0. So what this implies? Xk is equal to 0, but we have assumed that xk value is greater than or equal to 0 for every k. So which is a contradiction. That is, what you are getting is xk is less than 0, comma, which is a contradiction, to our assumption. What is that? Xn is greater than or equal to 0 for every n. Thus we get our x is greater than or equal to 0. So we have proved the theorem. Next we will have another theorem, 3.2.5 theorem. 3.2.5 theorem. If x equal to xn and y equal to yn are are convergent sequences of real numbers and if xn is less than or equal to yn for all n belongs to n, then limit of xn is less than or equal to limit of yn. So what this theorem says? This theorem says that if xn and yn are two convergent sequences of real numbers with a condition xn is less than or equal to yn for all n belongs to n. That means every term of xn, or we can take if it is x1, x2, x3, x4, etc. and this has y1, y2, y3, y4, etc. then each term, this term is greater than this, this term is greater than this, like that. Okay, so every term is this sequence is containing greater terms. Okay, then what will happen? Limit of this sequence when I am finding, and limit of this sequence I have found means limit of this sequence should be greater than limit of this sequence. So for this we will make use the previous theorem, right? How to use it? By defining a new sequence Zn that is equal to yn minus xn. So let Zn equal to yn minus xn. Then z equal to zn, right? Is a sequence with Zn greater than or equal to 0 for every n, right? Then by previous theorem, what you will get? Limit of the sequence Zn is greater than or equal to 0, right? That is, what is limit of the sequence Zn? Limit of the sequence Zn means yn minus xn is greater than or equal to 0, or that is, you will get limit of yn minus xn is y minus x, right, is greater than or equal to 0. So that implies, which implies y is greater than or equal to x, right? So this implies limit of the sequence yn is greater than or equal to limit of the sequence xn. So we have proved that one. Very simple one now. Next we will prove theorem from 3.2.6. Theorem 2.3.6. If x equal to xn is a convergent sequence, convergent sequence, and if a less than or equal to xn less than or equal to b for all n belongs to n, then a less than limit of xn less than b, a less than limit of xn less than b. If every term of a sequence is lying between a and b, then limit of that sequence is also lying between a and b. That's the meaning. Okay. So every term of the sequence lying between two real numbers, then limit of that sequence also lie between the two numbers. The proof, consider one part, that is a, sorry, a, right, not a less than or equal to xn for all n belongs to n, a set of natural numbers. Now consider the constant sequence. Now consider the constant sequence. The sequence is, I'm writing this as a sequence, a equal to a, 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 etc. Right? Now what you are having now? This every term of the sequence is less than or equal to xn, right? Now what we have to do? We can use the previous theorem, right? Then applying previous theorem to sequence a and xn, uh, we get, what we'll get now? See, this condition is already the a is less than or equal to xn. So we will get limit of the sequence, I'm writing as an. Okay, so limit of the sequence an is less than or equal to limit of the sequence xn. Now what is the limit of the sequence an? That is a, right? That is a is less than or equal to limit of xn. So we have proved that one. Now similarly we can prove that whenever your xn is less than or equal to b by taking the sequence b b b b etc. Right? Similarly, by considering the constant sequence representing as b, that's equal to set of b and that's equal to b b etc., we get the required result, right? And applying previous theorem, with the condition with the condition is xn is less than or equal to bn. For every n, we get limit of xn is less than or equal to b. Thus, we can conclude, thus we have a less than or equal to limit of the sequence xn less than or equal to b. This was the required answer. Next is an important theorem, 3.2.7. It is called skews theorem. S-Q-U-E-E-Z-E. Skews theorem. Skewing means applying pressure from this side, and applying pressure from this side means this material should be skewed, right? So when you are applying pressure, it will come like this, right? Applying pressure. So it is skewed towards to the center. That's the meaning. So let us see what's the significance of the name skews here. Suppose x equal to xn, comma y equal to yn, and z equal to zn. Three sequences are are sequences of real numbers such that xn less than or equal to yn less than or equal to zn for all n belongs to n, and that limit of xn is equal to limit of zn. Then the sequence y equal to yn is convergent and limit of our sequence xn should be same as limit of the sequence yn, and that should be the same as limit of the sequence zn. So this is called the skews theorem. So let us examine what is the statement. It says that we got three sequences. One sequence is xn, another sequence is yn, another sequence is zn, and the condition given is that xn is less than or equal to yn less than or equal to zn, right? Then what we are having now, if this is the condition and limit of the sequence xn equal to limit of sequence zn, that means limit of this sequence and limit of this sequence are equal, then this theorem says that then the sequence yn converges, this sequence converges, and these three will have the same limit. The three will have the same limit. So let us see how we can prove it. Proof: let sequence xn and Zn converges to W. Converges to W. That is, given epsilon greater than 0, we are making use of convergence of limit definition. Given epsilon greater than 0, there exists k1 belongs to n such that modulus of xn minus w is less than epsilon for every n greater than or equal to k1. Also, there exists k2 belongs to n such that k2 belongs to n such that modulus of yn minus w is also less than epsilon for every n greater than or equal to k2. Some other natural number. Now we can combine these two, right? By taking supremum of k1 and k2. Now let k equal to supremum of k1, k2. Then for given epsilon greater than 0, modulus of xn minus w is less than epsilon and modulus of zn minus w is less than epsilon for every n greater than or equal to k. That is, what will happen? That is minus epsilon less than xn minus w less than epsilon and minus epsilon less than zn minus w less than epsilon for every n greater than k, greater than or equal to k, right? Now call this as your equation 1. We want to prove that yn converges and yn also converges to the same w, right? Now given xn less than or equal to yn less than or equal to zn for all n belongs to n, then xn minus w, which should be less than or equal to yn minus w, right, which is less than or equal to zn minus w, right? Now from 1 we are having xn minus w is less than epsilon, taking this side, and when you are having this side zn minus w is less than epsilon. So taking these two part, we will get, then from 1 we get for given epsilon greater than 0 minus epsilon less than or equal to yn minus w less than or equal to epsilon for all n greater than or equal to k. So this implies modulus of yn minus w is less than or equal to epsilon for every n greater than or equal to some k. So this will exactly give you the convergence definition of the sequence yn, right? Now since your epsilon is arbitrary, we get the sequence yn converges to w. That is limit of the sequence xn equal to limit of the sequence yn equal to limit of the sequence zn. Okay, so we have proved Q's theorem. The Q's theorem says that whenever you are having these sequences xn, yn and zn, the conditions xn less than or equal to yn less than or equal to zn, then if xn and zn having the same limit means yn also converges and limit of yn is same as limit of xn. Next we are having a not. Not since any tail of a convergence sequence has the same limit as the these theorems 3.2.4, 3.2.5, 3.2.6 and 3.2.7 can have a version in terms of tail of the corresponding sequences. Tail of the corresponding sequences. What this says is that suppose we are taking Q's theorem, right? See, in Q's theorem, we are having the sequence x equal to xn and y equal to yn, and zn is a sequence of real numbers such that this condition is held for all n given for n is given. Instead of that, we can replace this with an m tail. After the m tail, if this condition is held, then after the m tail, limit of the m tail of the sequence xn is same as limit of m tail of the sequence zn. Then the m tail of yn is convergent, and that will converges to the same limit. We can say in that fashion also. So like that, we can modify these all theorems using the tail of a sequence. So today's class, we will discuss some of the theorems on limit of sequences. The first theorem says that whenever limit of a sequence is when the terms of a sequence are greater than 0, the limit of the sequence is also greater than 0. Next theorem was when you are having, see, every terms of the sequence are lying between a and b, the limit of the sequence is also lying between a and b, right? Before that, one more theorem was that if xn less than or equal to yn for all n, the limit of xn is also less than or equal to limit of yn. And, if the terms are lying in between a and b, then limit of the sequence also lying between a and b. And after that, we have seen Q's theorem. Q's theorem says that if xn, yn and zn are three real sequences and xn and yn converges to the same limit w or anything, then the limit of the sequence yn also exists, and limit of the sequence is same as this limit. And the last note, we have noted that this all theorems can have a uh, version in terms of tail of a corresponding sequence. Okay, with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.